Okay, so we start. Okay, so today we begin a new topic altogether. So far we have been discussing random variables. Say one random variable, then two random variables, then multiple random variables, and all that. Okay, and of course there are probability density functions, probability distribution functions, and various relations and properties associated with them. Now we use those concepts to now explain or to interpret various natural phenomena, and that takes us to the study of random process, or also called, which is also called stochastic process. What is a stochastic process? Essentially, you remember how we define random variables. I mean, there was some experiment. It's not that it could be a really experiment, but it's just a kind of, it's just a axiom that okay, I mean there is an experiment and there are various outcomes that are coming out depending on the trial, and with each outcome you assign a value to a variable. So that variable is then called a random variable. Similarly, suppose we have got some experiment that is going on, and every trial there is some outcome, okay, and with each outcome is there is first experiment, then maybe say theta is a set of all outcomes S. S is a typical outcome. So whenever a particular outcome, an experimental when a particular trial takes place, you get some outcome S, and depending on what you get, you assign a value to the variable X, and that variable is called then a random variable. Right, random variable X. But instead of assigning a value to the random variable, suppose depending on the outcome S, we generate a function x of t, okay, a particular function. That is, we assign, instead of assigning a value to a value to this outcome S, we assign a function x of t, okay, to S. So every time you get a new outcome, you get a new function. So that means as experiment goes on, you get some, every outcome you get some new function or some other function, another function. So these are kind of not random variables, but random functions. This random functions, actually, this set of all random functions as are possible here, they constitute one stochastic process here. I'll give examples to elaborate this. So that means you generate a function x as a function of some t, variable t, and also it depends on the outcome S. So for a particular outcome, you have one particular function. For another outcome S, you have another function. So depending on the experimental result, you get a waveform. So there is no fixed waveform. So waveforms vary. Okay. For example, suppose there is a microphone, and I say IIT. Okay, this is recorded and then displayed on an oscilloscope. You get some kind of waveform. So every time I say IIT, you get some waveform. But using your intuition, you can easily understand that even if the same speaker goes on saying IIT, again IIT, again IIT, again IIT, every time you will not get the same waveform, because the speaker is speaking. He's after all, he's a human being. He's not a robot. So things are changing. In his throat, in his voice generation mechanism, everything is changing little bit on each trial. As a result, the waveform which represents the sound IIT, that also varies. So that means with each trial, with each outcome, here outcome is a particular word, the way it is pronounced, that is the way IIT is pronounced, a particular, that particular way is one outcome. Okay. So with that, a waveform is associated. Next time I say the same thing, okay, but things differ a little bit, because as I told, I am a human being, I am not a robot. I get another outcome and the waveform changes. Okay. So set of all such possible waveforms that correspond to all possible outcomes, actually, that together is called, actually that set is called ensemble. I will come to that. Okay. This process of assigning random functions, these functions to outcomes, is called stochastic process. Okay. In general, in general we have got, so the family of all these functions belonging to all possible outcomes, they constitute the random process. Okay, so I will just say x t comma s. Let me make it more clear now. If I just say x t comma s is a random process, that means these things. So there is some experiment, and every time some the experiment is conducted, there is a trial is made, a waveform is generated, and that waveform is some function x t comma s. Okay. But stochastic process means, or random process means, every time you perform the experiment and you get a new outcome, the waveform changes. It is not a fixed waveform in general. Okay. Ensemble, this is another definition. For all s. Okay. That is, you consider the set of all possible waveforms. All possible means depending on the all the outcomes. For one outcome, one waveform. For another outcome, another waveform. So I am collecting all possible outcomes and therefore collecting all the waveforms. So the set of all possible such waveforms for this experiment, they form one set, and that set is called ensemble for the stochastic process. Stochastic process is this phenomenon. So it might appear to be a little vague. Stochastic process, the definition, actually it is this phenomenon. What is the phenomenon? That this phenomenon of obtaining random functions depending on the experimental outcome. For a particular experiment, there are several outcomes possible. Every time you conduct the experiment, you get one outcome or another outcome, and then you get one waveform or another waveform or another waveform. This phenomenon is called the stochastic process. A particular waveform, suppose S is a particular outcome, and for that outcome you have got a particular waveform x t comma s. For that I will call that particular waveform, that specific waveform for a particular s, a sample function. So ensemble consists of all possible sample functions. Okay. So sample function is a particular waveform, okay, for a particular experiment outcome. So just to sum up, we have these points. What is a stochastic process? Stochastic process is a family which is also called ensemble of functions x t comma s, where s stands for experimental outcome. Okay. And this family or ensemble of all these functions, actually ensemble or set, so they constitute the stochastic process. Okay. Then for one specific case, sorry, one single function. Obviously, for a particular outcome, you get only one function, a specific function. Okay. Called sample function. Okay. Then on the other hand, x t comma s for a particular t is what? Is a random variable. This is very important. Is a random variable. Why? Simply you have fixed a value point t. So, at that t for one particular experimental outcome x, you have one value of this function. Next time the outcome changes, you get another value of the function. So, this then corresponds to a random variable only. It takes various values depending on the particular outcome at hand. So, this is a random variable, right? And if t and s both are fixed, then it is just a number. If we are fixing t also on particular time and one particular experimental outcome only, then there is nothing random about it. It is just a number. Okay. Some examples. There are some processes which are called regular processes, and some processes are called predictable processes. I will just touch upon this. Suppose we consider the Brownian motion, that there is a fluid and some particles are moving at random and they are colliding with the molecules and again changing their direction randomly. Okay. So, here if I try to describe the motion of a particular particle, obviously it is random, it is every time changing its direction, also speed, it is random. Okay. But it is not given by some fixed set of parameters and all that. Okay. Also, it is not predictable, like in the sense that if you know its past trajectories, you cannot say what its future trajectories could be. Okay. So, this is actually a pure regular unpredictable process. But suppose I give you a signal, a process like this, x t is say a cosine omega t plus phi. I have omitted the variable s here, I mean it is quite implicit. Here this a and phi, that is amplitude and phase, suppose they are random variables. That means every time you conduct the experiment, here actually there is no particular experiment, every time suppose you receive a waveform, receiving a waveform is the experiment, the trial of the experiment. Okay. Maybe you get a particular ray, or every time you say generate a waveform, maybe by an oscillator, you get a particular ray and particular phi, and therefore particular x t. Okay. So, for a particular ray and phi, that is for a particular experimental outcome, or for a particular experiment, x t is fixed, you get one waveform. Next time a and phi changes, you get another waveform. But nature of waveform is, there is something interesting here, that the nature of the waveform still remains sinusoidal. In this case, this waveform, I mean I will not call it regular, because this random process is actually generated, is just completely described by few parameters, just few random parameters a and phi, omega is fixed. So, if a and phi are given to you, you know what it is. And then it is also predictable for its past, in the sense that suppose you know x of t, I mean for one period fully, or maybe x of t up to some point of time, say t naught. Then since it is sinusoidal and therefore periodic, it is easy to see that then you can easily predict all the future values, that is for all t greater than t naught also, the waveform is known to me without any error, that I know because of the periodicity. So, this process is called predictable process. Okay. So, we will talk about this more in detail, predictable processes and regular processes and all that later. Okay. Then we carry forward our previous notion of probability distribution functions and probability density functions to stochastic processes. Earlier we defined these things for random variables. Now obviously the question comes that when you have no particular random variable but a function, then how will you apply the theory of or the notion of probability density function and probability distribution function and all that. Here I would say that suppose I am getting waveforms like this, a particular waveform, and I look at a particular time t, then obviously the value that I find, this is the waveform x t, I am not writing x t comma s but it is implied x of t, there is x t comma s, s is for the particular experimental outcome. So, for a particular sample function, I get at a specific t, I get this much value for the sample. Next time with another experimental outcome, the waveform changes, this value also changes, and likewise. So, as I said earlier, that for if t is fixed, then x of t comma s, or simply x of t, if I just ignore s for the time being, is a random variable. So, on that random variable, I can obviously define what is known as probability distribution function, probability density function. So, that means we can define simply like this, that capital X, and for a particular t, x is nothing but probability of this random sample x t taking value less than equal to capital X. So, x of t is a random variable as long as t is fixed, and then probability of its taking values less than equal to capital X is indeed the probability distribution function. So, it is a function of the capital X you have chosen, but you have also put t as another variable, because obviously this depends on the t you have chosen. So, it is very much same as before, but only thing is, I mean, it is dependent on two factors now. One is of course the capital X that you choose, another is the time variable, because this probability distribution function is now varying over, if you call t as time, is varying over t, varying over time, okay, at various points of time. And of course, I forgot to mention that the waveforms that you are seeing here, these are actually continuous random variables, or continuous random process, not continuous random variable, continuous random process, in the sense that the variable t is chosen from the entire real axis, which is a continuous, I mean, which corresponds to I mean, continuous t. This, if t is taken from the entire real axis, then obviously t is a continuous variable, and x of t is called a continuous random process. On the other hand, if t is taken to be integers on this axis, say t equal to 0 or t equal to 1 or t equal to 2 and like that, but only those integers, specific integers, then it is a discrete time random process, also called random sequence. Or in our examples, we are considering continuous time random processes, but the this same notions can be carried forward to discrete time random process also very easily. Okay. For instance, if you want to find out this probability distribution function for a random sequence or for a discrete time random process, then we will not have t, because t is not taking any value. We will have rather n, because t can be an integer n. T is integer, so t can be 0, 1, 2, dot 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 up to n. So, for a particular integer point n, we will have f within bracket x comma n, or maybe you can change your style, you can put n in the subscript, f n within bracket x is nothing but probability of x n, because then it will not be, I will not denote it as x t, I will be calling it x n. So, probability of x n for a fixed n, probability of x n less than equal to capital X. So, I write it actually. This just shows that these concepts can be easily generalized to the or extended to the discrete time case. So, for a discrete time process, say x n, n is an integer. So, I can have at n equal to 0 some value x 0, n equal to 1 at x 1 and like that. So, depending on a particular experimental outcome, we get one sequence. Next time the outcome changes, we get another sequence. I say sequence and not function. Earlier I had function, now it is just sequence, because it is discrete time. But in the same manner, we can define its probability density, probability distribution function, that is f capital X, of course, and you can put a n here, or maybe you can put a subscript n, either way, it shows dependence on n. There is nothing but probability of that particular sample x n, in a sample x n less than equal to capital X, just analogous to the continuous case. Okay. So, if we have got probability distribution function, obviously you can have the probability density function also. So, P, again I am back to continuous time random process. So, P say x t is nothing but derivative of since I am deriving, I can put small x again back here, not a specific capital X, but again just general variable x, and differentiate it with respect to, in fact, I would rather, for correctness, I would put partial derivative, because it is a function of two variables. Okay. This is a probability density function. The meaning is same as before. That is, if you want to find out the net probability of the random variable x lying within a strip between x and x plus dx at the same time t, of course, then that probability will be this density function times dx. Okay, same notion, but everywhere there is a dependence on t, because I have targeted the random variable located at time point t. Okay, that is a particular random variable. Actually, random process, you can, any continuous valued random process you can view also as that uncountable infinity, uncountably infinity of random, random variables. Okay. Let me explain actually what is countable and what is uncountable. Of course, if you have got a finite set of numbers, 1, 2, 3, or maybe 10, 15, 17, 21 and all that, then obviously it is countable, you can count. Then again, you can make the set infinity, but still it is countable in the sense, if it is say 0, 1, 2, 3, 4, 5, dot, 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 it is countable, but that will be called countably infinite. First one was countably finite, the next one is countably infinite. But when it comes to, so in the case of discrete time random process, that was countably infinite, that was corresponding to countably infinite set of random variables. Okay. At every time point there is a random variable standing. But when it comes to this continuous valued, it is not countable, it is continuous, between any 2 points, again there is, you have got infinite points. That is a case of continuous random variables, or continuous variables, right. So, a continuous valued random variable, random process, continuous valued random process is nothing but a non-countable infinity of random variables. Okay. And then if you have these things, we can again, just use the previous notions in the same way. For instance, so far we have defined the probability distribution of just one random variable x of t located at a particular t, and corresponding density also defined. Now we can make it two random variables, that is, we can define joint distribution and joint density. You can find out, we can consider say a particular sample function, say t1 and t2, and fix t1 t2, fix t1 t2. So, this x of t1 and x of t2, they are two random variables, because depending on a particular waveform or particular outcome, they take some values. Next time the waveform changes, they take other values. So, they are random and they are jointly random, they are varying jointly hand in hand. Okay. So, that means we can define in an analogous way their joint distribution and joint density functions like that. So, but then joint distribution function, it will depend on two things, x1, x2, but also the two time points t1, t2, because the definition, as you understand, will be probability of two things, joint probability, that is x t1 falling below x1, x t2 falling below x2. Okay. And therefore, corresponding joint density function will be, now again I bring back small x1, x2, because I want to define the probability density not with respect to a specific x1, x2, but the general variables small x1, small x2. This is nothing but del square f double differentiation del square f x1, x2, t1, t2. Remember t1, t2 they are not changing, they are fixed, okay, but they are just present everywhere. Okay. Then again in the same manner you can say, I am just showing that all our previous notions of probability density and distribution apply here in this manner. If you just view xt1 and xt2 to be two random variables, varying jointly. So you can easily see, I can write some of the further some other identity also, that is if x1 t1, you can always write as if x1 the joint distribution, x2 taking and this infinity t1 and any t2. Okay, because this means there is another variable, this is joint distribution, this is single distribution. In the case of joint distribution, if the other variable is x2 and x2 lying below infinity, that covers all possibilities of x2. So obviously you get just a function of single random variable, I mean you get a single random variable, probability distribution function, not joint. Okay, this you have done earlier. Similarly, P if you take any joint distribution, joint density function, but integrate it with respect to x2 from minus infinity to infinity, obviously x2 will disappear, you get the single density function, not joint. Okay, obviously. So therefore, in a similar manner, I can define mu t as the mean of the random variable x t. There is nothing but E of x t for a particular t, which is nothing but for a particular t the probability density multiplied by the value x, integrate with respect to x. Okay. Similarly, you can define, of course, I am assuming real valued case, but we have to generalize this to complex, that I will do little later. Similarly, you can define autocorrelation or T1, T2. This is strictly for real case. For imaginary case, I have to bring some complex conjugation somewhere. That we will do little later, just to see what it is. It is nothing but we have got two random variables xt1, xt2. It is just the expectation of the product. In the real valued case, it is simply the product, no complex conjugation anywhere, and expected value, which is nothing but double integral minus infinity to infinity. Suppose it takes x1, the other one takes x2. This product is multiplied by the joint density, but t1, t2 will continue, and dx1, dx2. Okay. You can also see that this is a function of two arguments. So, you can plot it in a three-dimensional plot, and if you take the straight line t1 equal to t2, say equal to t, t1 equal to t2, if you put and if you call it t. So, for any t1 equal to t2, you have got E of xt1 again xt1, okay, which is nothing but the expected power of the random variable at a point t1. That is, if t1 equal to t2 equal to t, then or t1 t2 leads to simply or t comma t, which is E x square t, which is nothing but expected power. X square t is the instantaneous power. That is for the particular waveform, the power at time point t. Then if you average it over the entire ensemble, that is, take it for all the sample functions belonging to the ensemble and average out, then there is the expected power. So, expected power at t. Okay. In a similar manner, you can define cross autocorrelation autocovariance C is nothing but xt1, this random variable, minus its mean times, again I am doing for the real valued case. In the complex case we will generalize, we will bring in some conjugation and all that. And if we expand it, we have done it earlier, we just had x and y. It is very easy to see, this is becomes nothing but or T1 T2 minus the product of the two means. You can ask this question as to, if R t comma t is what is important to us, there is a power, why do we consider a more general function R T1 comma T2? Because we always consider this function R of T1 comma T2 as if R is a function of two variables. Why it is so? Why not just R t comma t? Answer is, answer is, suppose I am passing a random process through a linear system and I want to find out the power and the output, say. For the matter, suppose the system just takes one sample, another sample and adds. It is a linear system. It just takes two samples at a gap of T1 minus T2, adds them and gives you the output. Suppose this is the output. If you want to find out this, so if you just square this up, you will get, first if you square it up, you get x square T1 plus x2 square T1 plus twice xt1 xt2, then put expectation operator. Apply the expectation operator on each of the three terms. Obviously, what you get is R T1 comma T1, then R T2 comma T2, but also twice R T1 comma T2. So, this is where we need it. Okay. Some further examples. If you are given a deterministic waveform f of t, even that can be viewed as an extreme case of a random process. That is, this can be viewed as an extreme case of random process. It means that suppose we are conducting experiments, okay, we are conducting, every experiment leads to the same waveform. That is, with every outcome the same waveform is associated. That means for a particular time point say t, x of t is nothing but the value f t. So, x of t always takes the value f of t with a probability 1. Okay, this is the meaning of this. Okay, because every time the experiment gives us to the same waveform. So, x of t takes the value f of t, a particular value, with probability 1. This is the meaning of this. That means actually mathematically E of x of t, which is nothing but E of f of t, but f of t, x of t always takes the value f t, sorry, In fact, this is not required to write this. X t always takes the value f t. So, expected value of x t also is f t. Then it is f of t1 for a particular experimental outcome, f of t1, f of t2, but for any outcome also it is f t1, f t2. So, if you take the expected value, this will take the x t1 will take the value f t1 with probability 1, or this product will take the value f t1 into f t2 with probability 1. Okay, so, if you multiply with the probability density and integrate, you will get only f t1 into f t2. Okay. This is a special case, an extreme case of a random process where the experimental outcomes yield the same function only always, or give it, put it in a different way, given a fixed function, deterministic function we call it, deterministic function, we can still view it as a special case of random process where all experiments or all trials lead to the same function. Okay. On the other hand, consider this, that suppose you are given, I am coming back to the same example, a cosine omega t plus phi, a and phi random variables given, they are mutually independent, that is statistically independent. And phi uniformly distributed over minus pi to pi, meaning P of phi, and this is phi axis, it is like this, constant from pi to minus pi. Obviously, area has to be 1, so height is 1 by 2 pi. This, as I told you, this x of t is a random process, because every time you generate it or you make the experiment and observe it or generate it or whatever, you get, because of some new a and new phi, you get a new waveform. They may appear to be same because they are sinusoidal, but actually they are different because the starting phase is different, amplitude is different. So, it is a random process. Okay, but I told you it is a very special kind of random process, it is a predictable random process. So, if the entire past is known, or at least one full period is known, entire future can be predicted without any error, because it is periodic. Okay. Now, in this case, we can just again find out, mean and autocorrelation and all that. Okay. In particular, the autocorrelation. What will be the mean firstly? What is the mean? For a particular t, what is mu t? E of x t for a particular t, that is E of a cosine omega t plus phi. So, actually you have to multiply this by the probability density, joint density of a and phi, and integrate, double integral over the entire range of phi and entire range of a. But we are given the fact that a and phi, they are statistically independent. So, that joint density between a and phi is nothing but a product of the probability density of a and probability density of phi. So, that means this is nothing but E a, because the probability joint density will be then broken into two parts, probability density of a into a, integral with respect to a, that goes on one side, and probability density of phi times cosine omega t plus phi, and one integral from minus pi to pi, because phi is from minus pi to pi, that is another one. Okay. These two give two separate expected values. Okay. I repeat again, how to calculate the expectation? First, remove this E and all that, multiply this thing by the joint density of A and phi and a double integral with respect to A and phi. But the joint density is nothing but product of individual densities of A and individual density of phi, because they are statistically independent. So, double integral can be separated into product of two integrals. One of them is just with respect to A multiplied by its own density, another one is cosine omega t plus phi multiplied by the probability density of phi. Okay. That obviously gives rise to this. Which will give, I do not know what is E of A, some value, because we are not told about the probability density of A. So, we just keep it as E of A, but here we multiply cosine omega t plus phi by the probability density, that is uniform. So, value is 1 by 2 pi over what range? From minus pi to pi. That was the probability density, uniform from minus pi to pi, and within that range probability density of phi is taking the value, constant value 1 by 2 pi, which goes outside the integral. Now, if this integral, this is sinusoidal integral, right? It is varying with phi, and you are integrating it over one full period of phi from minus pi to pi. Obviously, its sinusoidal, so integral will be 0. You all know any sinusoidal function when integrated over its period, whether it is sine or cos, whatever, it leads to 0. So, this will give rise to 0. So, mean is 0. Okay. This gives you an idea about how to carry out these jobs actually. How about autocorrelation? So, you then take two time points t1 and t2 and multiply. Obviously, there will be a squared term, okay. That will give rise to a separate E of A squared, because of reason I have already explained, because A and phi they are statistically independent. So, joint density will be broken into, will be written as a product of two individual densities, one with respect to A, that will come with a square integral. So, that will give rise to E of A square. Another term will be expected value of the two terms, cosine omega t1, sorry, then cosine omega t2, again same phi. So, E of A square, and we break it as two things, half, and this expectation, you know, it is nothing but multiplying this by probability density of phi and integrating. Probability density of phi is 1 by 2 pi within the range minus pi to pi, and otherwise 0. So, it is nothing but 1 by 2 pi minus pi to pi. Why this half? Because cos A cos B is nothing but half cosine A plus B plus cosine A minus B. Okay. So, this will give rise to two terms, cosine omega t1 plus t2 plus 2 phi plus cosine just omega, phi cancels now, t1 minus t2 d phi. You see the first term cosine omega t1 plus t2 plus 2 phi, you are integrating with respect to phi. So, this function actually is this is now actually a function of phi. So, within the period minus pi to pi, this function completes two full periods, because we have 2 phi here, and obviously integral of 2 full periods is again 0. So, first term gives rise to 0, second term has no phi left. So, this term can be brought outside the integral will give rise to 2 pi and 2 pi cancels. So, you simply get half E square cosine omega t1 minus t2. So, if T1 and T2 are same, say equal to T, then cosine this value becomes 1 because this is 0, and obviously the power in that case will be half of half times E of mod a square, E of a square. Okay. It can be easily generalized to the complex case. Anyway, remember, random process is completely characterized random process say x t is characterized by its nth order okay, where T1, T2, Tn they are arbitrary points, and again n is taken arbitrary. So, this is true for all n and all possible choice of T1, T2, Tn, then this is completely characterized. Okay. Similarly, if you are given two random processes x and y, they are completely characterized by the joint distribution of this, that is f of this is joint distribution x1 to xn, similarly y1 dot 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 ym, t1 to tn, this corresponds to x1 to xn, and some other points t1 prime dot 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 tm prime, they corresponds to this. Again, for arbitrary choice of t1 to tn, for all possible choices of t1 to tn and t1 prime to tm prime, and then for all n and m. Okay. But anyway, this is more theoretical. In practice, we are more bothered by the moments, mean and autocorrelation or autocovariance. We have already seen it. We will just give the more generalized definition now, which is applicable to the case of complex valued processes. Complex valued process means ZT, actually at every point of time it takes a complex value, some complex value. Okay. So, you can also view it as some kind of summation of two waveforms. One is a real waveform, another waveform corresponds to the imaginary part. Okay. For this kind of processes, mu t remains as before, E of say ZT. But how about R T1, T2? Here you take ZT1 into Z star T2. Why this star comes, because we all know that when T1, T2 are same, this should give rise to power, expected power. Suppose T1 and equal to T2 equal to T. So, we have got RT comma T, that should give rise to power, expected power at a point T. The power is real. If I do not put the conjugate here, I simply get ZT whole square, which is again a complex number. Expected value of that also is a complex number. But if I put star here, then at T, we have got just mod ZT square expected value, which is real. Okay. Okay. That means in general, suppose R T1 comma T2, say for a complex process is given Z then this is called a positive definite positive definite sequence. After all, the positive definite function, sorry, it is not sequence. In the case of discrete time process, it would have been a sequence, because I would have had some index n and m which take integer values. Here T1, T2, so it is a function of two continuous valued random variables, continuous valued variables T1 and T2. So, we call it positive definite function. This implies for any non-zero sequence AI, I can be 0, I can be 1, whatever you have, this is always satisfied. Summation over I comma j AI R T I comma T j A j star. This number is real and it is greater than equal to 0. In fact, there is called non-negative definite function. If it is strictly greater than 0, okay, I would call it non-negative. What does it mean? That you have given the function R of T1 comma T2, you are just forming a sequence, you are picking up arbitrary I and j, I can be 10, I can be, and just some, and forming a sequence actually in the form of I. And if the sequence AI, you pick up any non-zero sequence AI, A0, A1, A2, A3 like that, where you only guarantee one thing, that not all A's, not all the values of this sequence are 0. Then for any choice of your I and j, if you carry out this summation AI or Ti, Tj, Aj star, this will be real and this is greater than equal to 0. This is obvious, because this thing is nothing but mod, if you carry out this, some choice of I. You see, this is more very general. I can be 1, then I can be 27, then I can be 31. It is not that I is 0, then 1 or 2, it is not. I is only integer. You are picking up and the discrete points are known to you. What is T1, what is T2, what is T3, okay. So, it is a very general thing. If you take a square, this is nothing but, I will just take a minute and wind up today. This is nothing but E of, but this we know, this number cannot be, this is a real number, it is mod square, an expected value. So, it can never be negative, this is always greater than equal to 0, but this thing is equal to E of and then A j x t j star, right, over j, this is over I, and this is nothing but summation, maybe you can put double summation or just write I over j, A I, A j are not random, so they remain as it is, x t I, x t j expected, x t I into x star t j, expected value of that, into A j star, and this is nothing but your R of Ti, Tj. So, this proves it. Conversely, it can also be proved that given a positive definite function, you can find out a random process whose autocorrelation function is given by this positive definite function. This we might show later. Okay, that's all for today. Thank you very much. Okay, so in the last class, we gave an introduction to what is called stochastic process. That is, earlier we used to consider random variables. That is, you have an experiment, and depending on the outcome of the experiment, the variable takes a value. Since outcomes are random, the variable takes values in a random way, and we call it random variable. So we studied single random variable, we studied double random variable, and functions of random variable and all that. They are probability densities and probability distribution functions. In the case of process, it was extended to functions. That is, depending on a particular experiment, you got just a function. Function could be continuous, function could be discrete, but a function discrete in time, a function emerges, and that function is then random because depending on depending on the particular outcome at hand, you get just one function, right? So that set of all functions, this is called the process. Okay, this phenomenon is called the process. The set of all possible such random functions is called the ensemble. Okay, you can just stick to a particular time point, maybe t or t1 say on the time axis. So at that point, every time you have the experimental outcome, you get one value because the function takes a particular value. Next time the value changes, so the value the value that this function takes, you will call the function x of t, then x of t1 for a fixed t1 itself is a random variable, and that is true for all such t1s on the time axis. So basically, a random process is nothing but an infinite collection of random variables which take different values depending on the experimental outcome at hand. Okay, so it basically is random functions. Then in the last class we also discussed the meaning of joint probability density, joint probability distribution functions given a stochastic process or random process. Okay, and then correlation, covariance. Okay, and related things also are defined. Today we will be considering a particular class of random process called stationary process.